the significance of maternal hepatic vitamin A stores and maternal dietary vitamin A intake in establishing vitamin A reserves in offspring. So a little bit about vitamin A. It's an essential micronutrient that we generally get through various animal products as well as colorful fruits and vegetables. And vitamin A deficiency is considered a global health concern and can affect up to 250 million people worldwide. And half of this is children under the age of 5. So this is incredibly important because vitamin A deficiency is associated with a whole host of complications, particularly ocular disorders associated with xerophthalmia, immune and epithelial dysregulation, and adverse developmental outcomes. And in fact, vitamin A deficiency is considered the leading cause of preventable blindness in children worldwide. And with that, approximately 250 to 500,000 children go blind annually as a result of vitamin A deficiency. So again, it is very much a global issue, a serious issue. And as you can see in this map, specific areas such as sub-Saharan Africa, India, the Philippines, Indonesia, and Mexico have the largest rates of deficiencies in children, particularly having percentages that exceed 30%. So vitamin A deficiency tends to affect those who have a higher nutritional demand, particularly pregnant women and developing children at highest risk. And so current vitamin A supplementation measures recommended by the World Health Organization suggest that settings that have a high prevalence of vitamin A deficiency or xerophthalmia should have supplementation programs for children aged 6 to 59 months. This is usually in the form of vitamin A megadoses through vitamin A capsules. So for children aged 6 to 11 months, this is a single dose of 30,000 micrograms of retinol activity equivalents. And then for children older than this age group, they receive doses every 4 to 6 months until 5 years of age of 60 micrograms of retinol activity equivalents. So all these supplementation measures have been very beneficial. Vitamin A deficiency is still quite a prevalent concern, and there are a lot of gaps in knowledge. So some of these gaps our lab is trying to understand is the relative importance of gestational periods and lactational periods with regards to vitamin A deficiency, and also the source, which we'll be discussing today. And then we'll also be examining in our lab the molecular mechanisms associated with vitamin A transfer into mammary milk and subsequently to offspring. So given the significance of developing adequate vitamin A reserves in early life, we're hypothesizing that maternal dietary vitamin A intake is the primary determinant of vitamin A reserves in offspring, independent of maternal vitamin A reserves. So for our study design, we wanted to look at the two sources of vitamin A transfer, so that being maternal hepatic stores and then the dietary intake. And then we also wanted to look at the two means in which vitamin A reserves are established in offspring. And this is through transplacental transfer during gestation, and then in the mammary milk during lactation. And so we looked at two groups of bulb C mice on varying diets. So one on a 25 IU diet or sufficient vitamin A diet during both gestation and lactation, and then one on a 0 IU diet or a deficient vitamin A diet during both gestation and lactation. And so we examined these pups over various time points, specifically at P1, which is birth, P7, which is at lactation, P21, which is at weaning, and then P35, which is 2 weeks post-weaning. We then took tissues from these pups and wanted to quantify the relative amount of vitamin A in the form of retinol and retinol esters using HPLC analysis. So for our DAM vitamin A content, we see first for DAM liver retinol ester that there is a slight reduction, but it's not a significant reduction in those who had a deficient diet versus a sufficient diet. We then looked at the DAM liver retinol levels, and these actually did show a significant reduction in mothers who were given a deficient than a sufficient diet. And then finally, we looked at the DAM plasma retinol levels. And as you can see in pups who had a sufficient or a deficient diet, there wasn't a large difference by any means. It wasn't measurable, so it wasn't significant reduction. And looking at the plasma retinol and then the liver retinol ester stores together really paints this picture of how maternal stores are not being significantly affected by a reduction in vitamin A in the diet. And this is relevant as a control because it emphasizes that our study is only evaluating the effects of diet on the reserves in offspring, and that the maternal stores aren't having a significant impact on this. So looking at the pup vitamin A content, we see that the P7 liver retinol has a significant reduction for pups who had a mother on a deficient than a sufficient diet. We do see a slight reduction in the P7 liver retinol ester levels. However, this is not significant. For P21 liver retinol and retinol ester levels, again, we see that pups who had a mother on a deficient diet showed a significant reduction. And this was also shown in P35 liver retinol and retinol ester levels, where pups who had a mother on a deficient diet, again, showed a significant reduction in vitamin A levels. So then we took a cumulative comparison of vitamin A content in offspring. And as you can see, looking at the liver retinol, there is this linear accumulation of vitamin A with time, which is inconsistent in pups who had a mother on a deficient diet. And then likewise for liver retinol ester, we see this, again, even more significant increase in the accumulation of stores that is inconsistent with pups who had a mother on a vitamin A deficient diet. And so this is really important because looking at P21 and P35 periods, the pups are weaned. So they're receiving vitamin A in the chow, similar to the pups who had a mom on a sufficient diet. But the difference being is that they're not getting the vitamin A during that lactational period at P7, and you can see how this has a significant impact in their ability to accumulate stores with time. So in conclusion, our study shows that the dietary aspect itself is most critical in establishing adequate vitamin A reserves in offspring, and that maternal hepatic stores alone aren't sufficiently compensating for this reduction in the diet, and so they alone are insufficient. We also saw that when we reintroduced vitamin A into the pup diet, so again, during P21 and P35, so weaning and 2 weeks post-weaning, the pups aren't able to efficiently rebound their stores. And so we don't see the accumulation levels the same as those who had mother on a sufficient diet. And lastly, taking this information, we can generate new knowledge of vitamin A transfer between the mother and the pup. And this has the potential to be translated into improved approaches to mitigate the effects of vitamin A deficiency in offspring. And I just wanted to give an acknowledgement. So special thanks to my PI, Dr. Robin Clugston, Sam Kinney, and the other members of the Clugston Laboratory. And then acknowledge that this research has been generously funded by the NSERC Discovery Grant.